Hello, everyone. It's my pleasure to introduce Conrad Plaut, who will be telling us about discrete homotopy theory and applications.
Okay, well, as we just discussed, I'm getting ready to finish being department head, so I really appreciate being invited to this conference. I think a lot of what I have done recently could be considered as sort of quantitative topology, but I've never done anything involving what I would call applied topology. The word applications there means applications to other areas of mathematics and not to data analysis or that sort of thing. So it's something I'm very interested in learning more about. And so I appreciate both being here and then giving, having the opportunity to talk about what I've been doing and how it might be related. Some of the theorems, again, these are applications within mathematics, but I think buried in the proofs are some techniques that might be useful in applied topology. And I can say some things about that maybe near the end. But I think right now what I want to do is just go ahead and kind of go through the basic construction, which is actually very simple. But first, the credits. So a lot of this stuff originated with topological groups and then uniform spaces and then metric spaces. I actually worked with my former graduate student, Jay Wilkins. And so those particular parts are joint work with him, some of that anyway. All right, so the idea is very simple. All right, so you take something called an epsilon chain. So this is just a finite sequence of points, and each point is of distance less than epsilon from its successor. All right, so you keep the points close. You define a basic move. So the idea here is lost my. Hang on a second. Yeah, so the idea here is that if you have an epsilon chain, right, and you fix the endpoints, and there are two things you can do, make it a little bit longer. You can add a point, right? So anywhere in the chain, just so long as you maintain the fact that it is an epsilon chain. And you can also remove a point, right? Just so long as, again, what you have left remains as an epsilon chain. Those are the two basic moves. And then if you take any finite sequence of those moves, that's something called an epsilon homotopy. All right, what you do next, so then there's a notation that's similar, right, for the usual notation for a homotopy class, but in this case, it depends on epsilon, right? So, all right, so then you basically imitate the construction of the universal cover, right? So you fix a base point, you take the set X epsilon of all homotopy equivalence classes of epsilon chains, starting at the base point. Then you have the endpoint map in the same way, right? And it's actually a little bit simpler because in this case, at least if you're in the metric case, then there's a uniquely determined metric on this. So you can sort of lift the metric to X epsilon so that this mapping is a local isometry. Okay, and in particular, there's a covering map. And this is, in some sense, the universal cover of X at the scale of epsilon. All right, and so then you can also define a version of the fundamental group. You just take all epsilon loops at the base point, and you define the group operation again as concatenation. And with this lifted metric, you have this nice fact that the fundamental group acts as isometries on this new space. And so this phi epsilon is a regular covering map. And I say this with quotes because there's some issues that can happen. For example, this might not be surjective. It's going to be surjective if and only if, as you can imagine, every pair of points in X can be joined by an epsilon chain. And also X epsilon may itself not be connected. And this is actually a little bit more important, right? And we'll see later how this can happen in some cases. But generally, you have this action, and so this mapping is a quotient as long as it's surjective by a sort of uniformly discrete action. All right, so this is basically a regular covering map in nice situations. So the idea here is that you parameterize these covers of X, right? And as epsilon gets smaller and smaller, it sees more holes, and then the universal cover unrolls. And so the sort of simply connectedness becomes smaller, right? So The most basic example, and it's actually a very important example in a certain sense, just take circle. And imagine that you have this sort of slider, right, for epsilon. And the circle, this is a geodesic circle, has length L. And so you've got some base point in there, right? And so somewhere up here is L. Now, if your epsilon is bigger than L, then think about it. Every chain is an epsilon chain, and every move is a basic move. And so every loop that you have can just be homotoped away to the trivial loop, just the base point. And so the space that you get is just the trivial cover, right? You just get a circle with the trivial group acting on it. Now, if you think about it, as you move down this slider, right? So when your chains are, say, very fine, then this basic move cannot cross over this circle, right? Because remember, you're only allowed, you have to stay with an epsilon chain, right? And somehow epsilon is too small to be able to move across this circle. That's kind of the intuitive idea here. And so at some point between L and as you approach 0, you're going to actually see that circle. Okay, so any thoughts about when that might occur? So there's going to be some place here where above here you have a circle, and then once you get below here, you get the universal cover of the circle. So any thoughts about where that might happen? And my slides are small enough that you can't read them, right? So, okay, well, that happens precisely at L/3, right? Because again, these moves involve triples of points. And so that's exactly, if you have a triple of points on here, it's not an L/3 chain, but you can subdivide it to make one, and that, right? But if you get any bigger, then of course you can homotop that away. Okay, so you see what happens. You have this slider, right? And once so you have just the trivial cover, and then you hit L/3, and then boom, you start to have the universal cover of the space. And so if you can imagine, if you take just a flat torus, right, and you have, right, two sides, right? So then what's going to happen is that you're going to start with the torus, right, the trivial cover, and then at B/3, it's going to unroll into a cylinder, and then at A/3, it's going to unroll into the plane. And if you have, if A equals B, then of course what's going to happen is when you hit A/3, it's going to unroll completely into the plane. And so in some sense you have a sort of a critical value of multiplicity 2, all right, because you're kind of having two things happen there. All right, so, and if you have a geodesic space with universal cover, all right, the nicest situation, then at some point you're going to hit the universal cover, right? So you're going to unroll, 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 and then for some positive epsilon, you're going to get the universal cover, and then you're basically done, all right? Okay, so this is a hint of what I hinted at before. It's something like this. So let's take an epsilon loop, all right? Now, if you make epsilon a little bit bigger to some bigger delta, it's still a delta loop, right? But you also, when you increase to delta, you get more possible homotopies, okay? Because you just have a bigger number, so there are more possible moves that you can make. And so an epsilon loop is a critical loop if it is not epsilon null, that is, it's not epsilon homotopic to the trivial loop, but if you make it arbitrarily a small amount bigger, then it is trivial, all right? It is null homotopic. Then that's called a critical loop. And so Jay and I defined the homotopic critical spectrum to be the set of all epsilon such that there is a critical epsilon loop, all right? Okay, and so the circle example actually shows up, right? Because in a geodesic space, these homotopic critical values actually correspond to the lengths of very specific closed geodesics that are called essential circles. And these are actually metrically embedded in the sense that the intrinsic metric in the circle is the same as the extrinsic metric in the space, all right? So you actually literally have the example I gave before everywhere that you have such a critical value. And so this tells you that the homotopic critical spectrum is actually contained in the length spectrum, which is the set of lengths of closed geodesics, all right? 1/3 of it, right? Okay. So now, Sormani and we independently did something that seems a little different, right? So there's this old construction of Spanier that involves constructing a covering space corresponding to a cover by open sets. And so they applied this to the cover by open balls, and they then got something that they called delta covers. All right. And despite the difference, you might think this is sort of fundamental, right? In fact, it turns out that these two particular coverings are exactly the same. They just have slightly parameterized it differently, right? So delta equals 3ε/2. These are both the same, okay? And they also, so they defined the covering spectrum along the lines of what I just observed for you, right? Which is that you have the slider and the equivalence type of the corresponding cover changes at certain discrete values, right? And they called that the covering spectrum. They also observed that the covering spectrum, which again differs by 3/2, right, is contained in 1/2 of the length spectrum. Okay, so summarize, right? The homotopy critical spectrum is 2/3 of the covering spectrum, which is contained in 1/3 of the length spectrum. All right, so that's where we are. Now, I want to, for this crowd, non-geodesic spaces, the geometry can give rise to phantom groups that persist for some interval, okay? So with geodesic spaces, this doesn't happen, but let me give a particular example. Let's just take a circle and take out a chunk of it, okay? So we're starting with a geodesic circle, we're taking out some chunk of length k, and we're taking the subspace metric, right? If we take the geodesic metric, we just get back the segment, okay? So we're going to take the subspace metric on this. And so if we imagine what happens with our slider, right? Okay, so, there are two important places, L/3 and K. K is the sort of size of this gap, right? And so when you're above L/3, you just have the trivial cover as before. When you get between L/3 and K, then something interesting happens. So you can, somewhere there's a base point, right? Since epsilon is bigger than K, you can hop right over that gap, okay? But on the other hand, you can't homotop it away anymore. And so it sees a circle from the standpoint of this pi epsilon group, even though it's not really a circle, there's trivial topology in this thing, right? And so that's why I called it sort of a phantom, right? Okay, so what happens in here, you actually get, right? So with the circle itself, you get just the real line, and then you get Z acting on it by translations. Here you get a broken up real line, which gets also translated by Z, okay? So in some sense, it sees this phantom topology for a little while, and then when you get down below K, your chains can no longer go across that gap. And so then it just becomes segment, okay? Just trivial, which is what you would expect topologically speaking, okay? But you have this little gap in there where it actually sees something geometric, even though it's not topological. Okay, and I will also say that, appropriate scales, I mean, these are just for metric spaces, right? So you can actually, even if you have a discrete space, as long as you don't get too small, if you get too small, you just get, a point, right? So, but you can still do this construction and get these groups. Okay, so the first application, again, this is kind of, my background is Riemannian geometry, but this is a quantification basically of a theorem of Gramoff, right? So Gramoff proved that the fundamental group of any compact Riemannian manifold of diameter at most d has a finite set of generators having representatives of length at most 2d and relations of this form. Now, what's interesting about this is that, as soon as you control the number of generators, that is, if you control K, then you can control the number of different isomorphism classes, because you can only choose between K cubed possible relations in order to form a group, all right? So one of the main applications that Jay and I proved is the following theorem. It's not done yet, but so first of all, Gramoff's theorem doesn't require a compact Riemannian manifold. It just requires what we assume here. So there's nothing new there. Semilocally simply connected compact geodesic space of diameter d. And then we have this parameter epsilon, which comes in mysteriously. And then again, the same conclusion that you have these generators with those relations. And what we were able to prove using the discrete homotopy theory is that we can actually control the number of generators. Okay, and so let me explain what these constants are. This one here is basically the number of classes in the fundamental group that have a small loop. They're represented by a small loop. So this is basically all small loops. And this is actually the number of epsilon over 4 balls it takes to cover X. So if you know about the Gromov-Hausdorff metric and Gramoff's precompactness theorem, if you have a precompact class, it precisely controls things of that sort. All right. And so, so that's just a description of what those things are. And so a corollary, we have that if you actually have a Gromov-Hausdorff precompact class of these things, that automatically controls this covering constant. And so then all you have to do is control the number of short loops, and then you can get a finite number of fundamental groups in that class. And so this actually generalizes a couple of fundamental group finiteness theorems, one of Anderson, and there are the assumptions, I won't go through those, and one of Shen-Wei. Actually, the one from Shen-Wei follows trivially from this, because once you get below the 1 systole, which is the length of the smallest closed geodesic, you don't have any short loops anymore except the trivial loop. Okay, Anderson's requires a little bit more work, and neither of these two theorems implies the other, but the corollary actually gets you both. Okay, now I want to talk about uniform structures because I think these are not used enough in mathematics. So they're a way to, it's like topology where you can measure to closeness uniformly at every point instead of just at individual points. All right, and so basically it consists of a collection of neighborhoods of the diagonal, symmetric neighborhoods of the diagonal, right, in the Cartesian product of the space. And so being close together means your ordered pair is inside that entourage. Okay, and those are the basic examples. And one thing I think might be of interest to this crowd, and that is entourages can be parameterized by several real parameters instead of just one, right? So you can sort of have closeness described more as kind of a multi-metric than you can than with just a single parameter. And so for metric spaces, you have the single parameter, you have these entourages, which are just, you're in there if your distance is less than epsilon. And so you can do exactly the same game that we did before, right? You just replace distance xy less than epsilon to x comma y is an element of E, and you get the corresponding maps that correspond to an entourage and not just to a real parameter. And then you get the groups, right? And then there's an assumption I won't talk about now, but you want to be sure these things are connected. And so such a thing is then called an entourage cover. So given an entourage, you get some kind of a covering space, always. Okay, so natural question. I'll go through this quickly because again, I mean, this is of interest to topologists maybe, but I don't know about applications of this particular thing. But what are these entourage covers? These are very special covering spaces, right? Okay, so first of all, if you start with a nice space and you have so remember, there's this Galois correspondence between normal subgroups of the fundamental group and regular covering maps, right? And so if the subgroup N corresponds to an entourage cover, then it's the normal closure of a finite set. And not only that, we can actually quantify the size of the generating set in terms of these covering constants. Okay, well, what about the other direction? Well, I don't really have a full answer in the other direction, but here's what I know. If M is a compact smooth manifold of dimension at least 3, then the entourage covers are precisely those corresponding to subgroups that are normal closures of finite sets. And this is not always true. So for the circle, the only entourages are the trivial cover and the universal cover. And I actually don't know the answer for surfaces, which may seem a little bit odd, but I don't know what the entourage covers are for surfaces at this point. Okay, so very quickly, one application, and this is sort of the original sort of very abstract esoteric motivation, was generalized universal covers. And so again, the point is that if you have delta less than epsilon, then every delta chain is also an epsilon chain. So you can have a mapping from x delta to x epsilon that just takes the delta class of alpha to the epsilon class of alpha, okay? and so, right, so you have X, you have X epsilon, you have X delta, right, like that. And this is like phi epsilon delta. Okay, well, as you might expect, it's almost trivial from the definition that these form an inverse system, okay? And we just call this the fundamental inverse system. And so this inverse system can be used to find generalized universal covering spaces for very general spaces, including solenoids. I mean, the simplest thing you can do is just take the inverse limit, right, of that. And if you have, for example, piano continuum that gives you some kind of a nice universal cover, generalized universal cover, the covering maps are not locally trivial, right? So they're actually pro-discrete actions instead of discrete actions, all right, in some sense. All right, and again, you can ask about that if you have questions later. Okay, so let's talk about spectra, right? So we already saw this relationship between the homotopy critical spectrum and the length spectrum, and this is a long history relating it to the Laplace spectrum in a Riemannian manifold. And again, I won't give more specifics about that, but I just want to talk about the history a little bit. And so, there was this question, can you hear the shape of a drum? And there's this Gordon-Webb-Walpert solution, well, negative answer in dimension 2. And they answered this by finding isospectral surfaces that have, so they distinguished between them because they have different length spectra. All right, so that was literally how they determined that they were different. Okay. And I will mention that DeSmet, Gornet, and Sutton, they used a method of Sonata to show that there are isospectral compact Riemannian manifolds, that is having the same spectrum, and they didn't consider the homotopy critical spectrum because those two hadn't been connected yet, but they showed it for the covering spectrum. So this is not a spectral invariant, basically, is what they showed, this particular spectrum. Okay. And their construction actually is what I used in the earlier theorem about manifolds of dimension bigger than or equal to 3, right? So they actually construct some nice Riemannian metrics where you sort of are allowed to predetermine the lengths of some loops that represent classes in the fundamental group, and then you can realize those lengths with a particular Riemannian metric, and that only works for dimension bigger than or equal to 3. Okay, now we have all these other covers, these entourage covers, right? So previously we just had these epsilon or delta covers, right? And these were all parameterized by the real numbers, but entourage covers, there are a lot more of them, at least in principle, right? Because you can choose any entourages at all and look at this. And so you can actually, there are these two playbooks, right? Sermani and we, you have these parameterized things, and they said, okay, we're going to look at when the equivalence type of the covering space changes. And Jay and I looked at these critical values, right? They end up being the same when we're talking about these nice parameterized covers, but in fact, they diverge actually when you consider entourage covers, all right? And so for Sermani and we, so again, you don't have this nice parameterization by real numbers, but you can consider, when one of these metric entourages is contained in an entourage, that's a measure of the size of that, right? And so you can send epsilon to 0 again. And what happens there is you have a whole bunch of entourages, and the covering spaces may not cover each other, but you have finitely many, and you can look at the places where the number of equivalence classes increases. And that gives you both a number, a spectrum, but also a multiplicity, depending on how much the increase is. So that produces a brand new spectrum. And the other thing you can do is define critical entourages. So remember before, a critical chain was when, it was epsilon homotopic, but if you made it larger, it was not anymore. It becomes null, sorry, backwards. So in this case, though, a critical loop is one that is not E homotopic, but is E bar homotopic, where that's the closure, okay? So that's kind of the replacement for making it arbitrarily larger. And entourages don't have to be open, right? And so that's why this particular thing works. Okay, so these spectra are actually new, okay? So, there are compact Riemannian manifolds where, the spectrum ECS is actually infinite, Okay, so it can't be contained in the length spectrum, but it is discrete above 0, 1. And in fact, the number of values can be quantified again using these covering constants. Okay, and then for a compact geodesic space, you have those relationships there. And again, I can go back and talk about those a little bit more, but these are all new and they differentiate differently among compact Riemannian manifolds. One important thing I mentioned at the bottom there is the marked length spectrum, which is the lengths of closed geodesics that are shortest in their homotopy classes. Okay, so that's yet another spectrum that one can talk about. Okay, and that's an open question, right? So I want to, getting a little closer to applications, just mention some things about fractals, right? So fractals have these resistance metrics, and again, I won't talk about where they come from, but the point is that there are no rectifiable curves in there, right? Except constant curves. And so, but they do have a Laplacian. So they have a spectrum of Laplacian, but without any lengths, you can't really talk about the relationship to the length spectrum, except that these new spectra are actually defined and finite. There's no problem, right, in talking about these particular things. And even more interesting, in a Riemannian manifold, the marked length spectrum is actually equivalently the lengths of discrete loops. Okay, it's the infimum of those lengths, or it's actually in a compact space, it's actually equal to the minimum, right? And this is finite in any metric space, right? So this is an advantage of doing away with curves, that if they're not rectifiable, you just don't care, right? Because this all reduces to sort of discrete quantities. All right, so then you can ask the same question, right? Now you can actually formulate it because you have a notion of the marked length spectrum in this space, even though there is no length. And so the question, is the old question answered by Carolyn Gordon, right? And so the question is, are there isospectral resistance metrics on fractals? Of course, you want to have the same underlying space with distinct marked length spectra. Don't know the answer to that. Okay, I want to talk briefly about weakly chain spaces that will lead up to the last application. I think I can make it there in 35 minutes because I'm going very fast, right? Okay, but so a metric space is called chain connected if for every x and y and epsilon bigger than 0, x and y are joined by an epsilon chain. Okay, so the shorthand for this is just that x and y are joined by arbitrarily fine chains. All right, this is actually classical people doing uniform spaces called this uniformly connected, but I like chain connected. It's much nicer definition, right? Okay, it's equivalent to the classical definition. All right, so we call the space weakly chained if, first of all, it's chain connected, and then for every epsilon, there's a delta such that if distance from x to y is less than delta, then x and y are joined by arbitrarily fine chains such that alpha, chains alpha such that the chain is actually homotopic to its endpoint set. Okay, so again, what does that mean? That means, if the distance between these 2 points is less than delta, so you have these 2 parameters, right? And so this just, the delta parameter tells you how far the points are. And so then it says that you can join them by arbitrarily fine chains so that you can homotop the chain away until you just get the endpoints. So I like to think of this as sort of an infinitesimal, semi-locally simply connected kind of thing, right? Okay. So my original motivation for this was to, try to understand sort of the weakest condition that you get a certain kind of generalized universal cover. But, oh yeah, so these are somewhere between solenoids and piano continuum, by the way. Okay. So I wasn't motivated by geometric group theory, but the first thing that I noticed was that this condition, which is very simple, is equivalent to a condition from classical shape theory called pointed one movable, which I had never heard of before. I don't really want to give you don't ask me for the definition because, well, it involves embedding in an ANR, and you can equivalently embed it in the Hilbert cube, and then it involves what you can do with neighborhoods around it. Okay, very complicated thing. And just showing that it's sort of well-defined takes a lot of work, all right? And I didn't know what I could use that for, right? So fine. Right? And so I want to say in contrast though, right? So the definition of weakly chained. So remember, you take a metric space, right? 2 slides gets you the entire definition. Slide 1 is what is a discrete homotopy, and slide 2 is the definition that you just saw. Okay, so very, very, very simple concept. All right. But then these guys showed in 2019 that there's a very old conjecture of Mihalich about semistability at infinity. Okay, so right. But this conjecture reduces to showing that the boundary is pointed one movable, which means that instead of going through all that now, all you have to do is show that it's weakly chained boundary. Okay, so just very quickly, I mean, one way to interpret the boundary is to fix a point and take the metric spheres, right? And then you have projection from one sphere to the next, and you also have the boundary, right, is the inverse limit of these. So one way to formulate this is that the boundary is the inverse limit, and then you have these projections down onto the spheres, okay? And so these spheres are actually weakly chained, okay? So then the question becomes, well, you have an inverse limit of weakly chained spaces. When is the inverse limit weakly chained itself, all right? And so we have this very simple definition, and so it's pretty easy to formulate when that happens, all right? And so here's a theorem. This is only just a start, okay? But this is something that one can do with this, okay? So if you take a Euclidean polyhedral complex with shapes finite, so there are only finitely many polyhedra going into it, right? And it has a connected boundary. And then you look at you forget about the boundary and you just look at the space of directions at each vertex, okay? So this is really just an infinitesimal or local condition here, right? If you know that that is a geodesic space, right? So actually it's a cat1 space, which remember doesn't have to be geodesic, right? It's not necessarily geodesic. But if you know it's a geodesic space, then the boundary is weakly chained and hence semi-stable at infinity. All right, so, okay. So there are these kind of famous examples called torus complexes of Croke and Kleiner. And so one can go back and look at the presentation of their fundamental groups and use some old fairly deep theorems of Mihalich to conclude that yes, they're semi-stable at infinity. But the prior theorem gives you an immediate answer, okay? Because you can look directly at these complexes and just see that the space of directions at each point is in fact a geodesic space. And I'm not an expert in geometric group theory. I'm just getting started in this now, but my understanding is that the answers to this question are generally algebraic, right? It has something to do with the algebraic structure of the group. And in contrast, this is actually geometric, right? That is, you are actually get in there and you just look at the complex, and if you can say this about the really the link at each vertex, then you're done, right? If you can check, and there's actually a somewhat weaker hypothesis that works in this, but this is the simplest one to state, right? Which is just that the link is a geodesic space. Okay, and so I think one can do better. Okay, so going back to the beginning of my talk, I'm about to be done being department head, and we'll have some more time. And I'm working, with a couple other people thinking about this, right? But I think there's a much better theorem. All right, I could be wrong. Okay, but I think there's a much more general theorem that can be proved. I won't say what it is, but because I want to think about it before everybody else, all these amazing people who are at this conference start thinking about it. I want to have a little time myself. So yes, and soon I'll have more time. So. All right. Oh, 9:35. Okay. So thank you, everybody. And now after that whirlwind, either you're just all too stunned or something, but there are if you have questions.
Yeah, thanks, Conrad, for the excellent talk. Let's all unmute ourselves and give a round of applause. There are questions?
Conrad, I have a first question way back at the very beginning. So you have a metric space, and for different values of epsilon, you have the epsilon universal cover. And I was curious if you could make an analogy with the stability of persistent homology, and if this analogy is true or easy or hard to formulate or false. But in persistent homology, you have a metric space, and you vary epsilon, you build Rips complexes, and you look at the persistent homology, and if two metric spaces are Gromov-Hausdorff close, then their persistent barcodes, are interleaved and all this. So do you get interleavings of covering spaces, and does this analogy follow through pretty nicely on the covering space side?
Yeah, so this is a great question. It's closely connected to this homotopy critical spectrum, okay? And so here's a very simple example. So it's not true in general, right? So you have to stay away from these critical values. And a very simple example is, so remember, if you take a circle, right, then, take a third, right, and then let's change colors here. And okay, so, right, so here we go, right. And so let me use another color. I'll tell you what I'm drawing here in a second, okay. Okay, so those yellow ones are a triple of distance L over 3 apart, right? And then the blue ones are also triple. I had to subdivide this in order to make it an epsilon chain, right? Because you have to have distance less than epsilon. Okay, so now let's take a smaller, that's a weird, okay, let's try something else here. Okay, let's take a smaller circle, okay? And then go ahead and increase the diameter. These are all geodesic circles, right? So as you approach this, right, the epsilon group of this smaller circle is always trivial, all the way up until you get to the next circle, okay? And so, in fact, these are not always stable or not stable in the Gromov-Hausdorff metric, but they are if you stay away from the critical values. And so you have to be just a little bit careful with that. But so Jay and I had another paper about this, right? Riemannian, we were also interested in what happens to the covering spectrum in the Gromov-Hausdorff metric. It's a very natural question. And so as long as you stay away from the critical values, and that's not as much of a problem as you might think, because you always have a little bit of room to tweak, because these values are discrete, right? And so, near any particular epsilon, if you move in the right direction, you have the same group, right? If you adjust downwards by a little bit, you have the same group. All right, so you always have that wiggle room, and so you always get convergence of these groups. The only problem is that you can't always line up the epsilon group in the limit with the epsilon group in the things approaching it. You have to move off the homotopy critical values, and then when you get close, you actually have isomorphisms between all of these groups. So the answer is not quite, but but yes. And I want to point out also, something I wanted to say in case somebody asked a question, but connected to this also is that you saw all those quantitative answers coming out, and basically those come about because close chains are homotopic. And again, you have to be careful. You have to give yourself a little wiggle room. But if you have an epsilon chain, right, and then you have another one, same endpoints, right? I keep changing to the wrong pen instead of the color. Okay, so and then same endpoints, right? Okay, so you can actually homotop one into the other, right? So if you have epsilon chains that are delta apart, you can, for example, when you're going along the red, you can detour there and go back, and then you can remove it. but you won't be able to stay within epsilon, right? The triangle inequality lets you stay within delta plus epsilon. And so kind of the formal statement is that if you have epsilon chains that are delta apart, then they are delta plus epsilon homotopic. But even so, again, because you have this wiggle room, you cover with balls, then, if you control the length of the chains, then you're controlling the number of ones that are within the distance represented by those balls. And so you get finiteness.
Thanks.
More questions?
Hi, can I ask a question?
Yeah, Leo, yeah, go ahead.
Hi, thank you very much for the talk. Very interesting. So I was wondering, my question is just very broad, like basically, do you have any connections to graph theory when the underlying space is a graph? And I ask because of two concrete reasons. So let me tell you why I'm talking about graphs. Okay. First of all, if you, for the first definition of these like epsilon homotopies and so on, if you take a graph with the shortest path distance and you take epsilon to be equal to 1, in that case, these valid moves that preserve homotopies, what you would be basically doing is like if each of the points are nodes in your graph, then you're basically moving from one node to another node that is a common neighbor of the two nodes that are adjacent to it in the chain. And I think that that notion has already been proposed, I think, independently as an alternative notion of homotopy for graphs. So and what you're doing seems to be like a generalization of that. So I was wondering if you've thought about that generalization.
Yeah. So I mean, again, if you start with the graph and you push epsilon to 0, then you're going to get the universal cover of the graph, right? Mm-hmm. But in between there, you're going to unroll cycles depending on 1/3 of their length, right? So I mean, for a graph, it's a particularly simple construction, right? If it's a finite graph, then of course you have basically you're going to have these critical values. They just represent 1/3 of the length of a particular cycle that opens up at that stage.
Right. Yeah, I mean, I was just wondering, perhaps because I'm also thinking, data science applications, perhaps for larger epsilons, this would perhaps like improve computations or something like that.
Well, once epsilon gets too big, nothing happens, right?
Right.
But
right.
If you have a sufficiently large graph, then you actually, I mean, you do, things happen, right? I mean, in between, when you get to the point where you just get the universal cover, I mean, you are going to get intermediate spaces in there, which are going to be graphs themselves, but possibly infinite graphs. Well, generally infinite graphs, right? Mm-hmm. And so I think for a graph, there's nothing particularly shocking here in the sense that all these covers are kind of known and exactly when they happen because you know what the size of this is. Now, if you want to go further than that, for example, just with simplicial complexes, I want to point out that in this proof of the theorem of Jay Wilkins and I, we actually, this is the one about the controlling the number of generators. We actually use sort of a modified Vietoris-Rips complex, two-dimensional one, right? Which is actually a geometric object. And so I think in some sense, yeah, I mean, what's interesting is that I think also, and again, I'm just thinking about this at the moment, right? So in a sense, with a graph, you can kind of forget the fact that it's a graph and just think about the vertices, right? Because you're still going to get basically the same thing there. Mm-hmm. And so this does allow you to kind of have like universal covers at various scales of data, right? Mm-hmm. That again is sort of a discrete space.
Yeah.
And so, I guess my point is that when you make a graph, right, you are making some decisions about, in your case, you're basically assigning the edge length to be 1 in each case, right? I think that was right. So that already kind of changes life a little bit from a metric standpoint.
Yeah, it definitely simplifies some things, I guess. But because, so I guess perhaps since perhaps a little bit more related to this geometric object you just mentioned. So personally, in my work, I work on an object that's closely related to the market length spectrum of a graph.
Okay.
Because if you take if you take epsilon equal to 0 going to 0, just standard definition of homotopy in a graph, you can easily prove that you can easily find what is the minimal length representative of each homotopy class.
Right.
This is otherwise known as a non-backtracking cycle. There's a thing called the non-backtracking matrix. I studied the eigenvalues of the non-backtracking matrix. And so essentially with the eigenvalues of the non-backtracking matrix, it's equivalent to knowing the the unmarked length spectrum.
Right.
And so what I've been trying to start to think about is how can I use the matrix to reach more information that is stored in the market length spectrum. Because I don't know, you may be aware of this theorem by Constantin and Lafont. Constantin and Lafont have proved that on compact geodesic metric spaces of dimension 1, so for example, 1 skeletons of simplicity complexes or graphs, the market length spectrum determines the isomorphism class of a very large chunk of the graph.
Right. Right. Go ahead.
So basically, my sort of one of my goals, like overarching goals, is to try to use the eigenvalues of the non-backtracking matrix to try to study the market length spectrum, because it determines the isomorphism class of the graph.
Right. And again, so what I'm doing, I think, doesn't give you for a graph much new information, although that could be famous last words, right? But because but one-dimensional spaces, whether they're graphs or not, are very special, right? In terms of the fundamental group really kind of determines them much more strongly than other spaces.
Yeah, exactly. I mean, I guess it would. I'm trying to think out loud about like what is the relationship between these like homotopy spectra that you're defining and the eigenvalue spectrum of this matrix that I'm looking at. So perhaps they're like two sides of the same coin, kind of thing.
No, I mean, we can certainly talk about it. Nothing occurs to me at this particular moment, but it might be worth talking about, actually.
Yeah, maybe I can send you an email and we can chat about it.
Yeah, that would be good. Yes, for sure.
Great, thank you.
Yeah, Conrad, let me just thank you one more time. I'm going to end the recording here so we can take a short break before the next talk, but everyone is welcome to continue chatting until the hour. So yeah, thanks again.